Welcome to Chapter 7, Control of Microbial Growth. Now, I've got to warn you right now, I think this is one of the most important chapters that we will be covering in this course because control of microbial growth is so important in clinical applications. So much of nosocomial infections that we deal with nowadays are not because we don't know to wash our hands. It's not because we don't know about the germ theory like our ancestors did previous to the 1700s. It's because we don't use the appropriate control method in controlling various assorted microbes. So, in your opinion, we'll probably be spending an unreasonable amount of time on this chapter, but no matter where you go on in your professions, whether you go into nursing, you become a doctor or PA or a dentist or a dental assistant or a hygienist, or even in your own home, if you know about the principles of control of microbial growth, you're less likely to have illness in whatever you're doing. It also helps you preserve food. Okay. Also, I should tell you that I spent a fair amount of my career testing disinfectants and tabletop autoclaves, testing gloves, all sorts of things that are used to control microbial growth. This chapter also fulfills two of the objectives for the course. First one is provide students with the knowledge necessary to comprehend the fundamentals of microbiology, including growth, and also objective number 4, which is to help you understand interactions and impact of microbes on humans and the environment. In this first part, we're going to be discussing the rate of microbial growth, actions of microbial control agents, and physical methods. In part 2, we'll cover chemical methods and microbial characteristics. When we're discussing the control of microbial growth, we need to know how many microbes are being controlled or killed by our control methods. So for that, we need to know the number of microbes. To do that, we use the same methods that we talked about in Chapter 6. This would be direct microscopic count, plate counts, that sort of thing. Once we've determined the number of microbes, then we can determine how well a control method works by determining how many microbes it has killed. Environmental influences also play a role in the rate of microbial death. For the sake of example, I'll use the example of a chemical disinfectant such as Lysol. Now, environmental influences are important to other control methods such as refrigeration, steam sterilization, etc. But like I said, I'm going to go with Lysol as an example. So one of the environmental influences is bioburden. Now bioburden is a technical term that refers to anything of biological origin that influences the activity of our Lysol spray. So we're talking about blood, vomit, saliva, etc. Biofilms also influence the rate of microbial death, influences how well Lysol can kill. When you have a biofilm, the gunk, the slime that is produced by the microbes to hold themselves together, keep out chemical disinfectants and also makes physical disinfectants have to work harder to kill microbes. So biofilms affect the rate of microbial death by slowing down the rate of death. Temperature also has an effect on microbial death. With Lysol spray, it has an optimal temperature in which it works, kind of like optimal growth rate in microbes, but in this case, with chemical disinfectants, temperature plays a role in how well they act. Some are set up to work at higher temperatures, some work better at room temperatures, some work better at lower temperatures. Temperature also has an effect on how susceptible the organisms are to kill, because generally speaking, if they're already stressed out by being above their optimum temperature, then their death rate is accelerated by physical methods. pH also plays a role in microbial death rate. Once again, Lysol works best at a certain pH. If things are too acidic, if things are too basic, that's going to throw off how well it works. For this next one, suspending medium, Lysol spray isn't a really good example because you don't mix it with anything. But there's many disinfectants that you do take and you mix it with something else to bring it up to in-use concentration. Now, with some of them, if you mix them with water, they're not going to dissolve real well, and they're not going to work very well, and they need to be mixed with a hydrophobic suspending medium. Most disinfectants, though, do well in a aqueous or water suspension. But once this ties into bioburden, if you're using tap water to mix up something, sometimes that will inhibit the action of the disinfectant, even though it's not a bioburden. It's an inorganic burden, still causes problems. Exposure time. Disinfectants, when they're tested, the standard is generally to test them at 10 minutes. I don't know why this is the standard, because nobody leaves a disinfectant sitting on a counter for 10 minutes. With sterilization methods, that makes more sense. You can pop something in a sterilizer for 10 minutes, see what the microbial death rate is. But with exposure time, generally speaking, we take a look to see what the rate of microbial death is for a set exposure time. And it's usually either 1 minute or 10 minutes. Some sterilization or control methods take a shorter amount of time, and so you don't have to use them for as long a time. Others take time to be able to penetrate the bioburden, the biofilms, the suspending medium, etc. The last thing that affects the rate of microbial death is the microbe itself. Some microbes are just tougher than others. Therefore, they're harder to kill, and we have to use more stringent measures, longer exposure time, all of that fun stuff. So all of these things go into determining rate of microbial growth, and they also are part of how we determine how well or how effective a control method is. Now at this point, if I may be allowed a little bit of reminiscence, I spent several years doing disinfectant testing and sterilizer testing, and we took all of these things into account, usually with temperature, pH, suspending medium. We would go with what the manufacturer recommendations were. But to add in bioburden, blood is the most convenient one, and it's the most common one out in a clinical environment. So when I was doing the testing, guess whose blood we used? Yep, you got it. We used my blood, and we also used the toughest microbes that we could. From previous years of testing, we found that if something would kill the toughest microbes, then why bother with the wimpy ones? We knew that a disinfectant or a sterilization method would kill the tougher ones, it'd kill everything else. Before we leave the topic of rate of microbial death, let's talk about how rate or score microbial death. We generally do this on a logarithmic scale. Now in this chart we have an arithmetic scale where for the time frame here we're looking at our exposure time as being 1 minute. In this case, in 1 minute we get 90% kill of our organisms. So with the arithmetic scale, we can see looks like there's a whole lot here. This is still 90%. Still 90%, looks like we've reached 0. So we generally represent this as a straight logarithmic line. Okay, so once we've killed 90% of the population, that is a 1 log decrease. Now, definition time. Federal standards are for sterilization, you're going to be killing all the microbes. So we're generally not talking about log decreases. We're generally talking about log decreases when we're talking about a disinfectant. A disinfectant is anything that will decrease the microbial count by 3 logs, or 99.9% of the microbes in the acceptable exposure time. If it's below that, and also if it's intended to be used on surfaces that people are going to be eating off of or putting in their mouths, we call this sanitization. Sanitizer is something that will kill less than 3 logs in the acceptable exposure time. So let's take a look at what happens when we have different starting numbers. In this chart, we have it all in logarithmic representation. Here we have a high microbial load. So even though we're seeing the same kill rate as for a low population load, you can see that we reached 0 in a short amount of time than we do for the high population load. It makes sense. If you start out with 1,000,000 organisms and you go to 10,000, that's a 1 log reduction. If you start out with 1,000 organisms and you have 1 log reduction, that goes to 100. So you reach your end point much faster. This is also why we have federal regulations about how many starting microbes you can have. For example, the FDA goes and inspects meat and slaughterhouses. If you have a carcass that has been all cleaned out, the feces and intestinal contents have been gotten rid of, the meat lasts longer. You have a low population load, and you don't have to do as many microbial control methods to keep it consumable for humans. For example, if you have a low population load on a steak, then you don't have to cook it for as long to kill all of those little nasties. Here's another one. If you have a dirty dish that has a high microbial load, then you have to treat it for longer, either by washing it or putting it through a commercial dishwasher to lower the microbial load to the point where it's non-hazardous for the bulk of the population. If you already have a clean dish, then you don't have to go to extreme measures. By the way, both of these are examples of removing bioburden. Now let's talk about the actions of microbial control agents. They generally fall into 2 categories. The first one, this is a hint, what would this relate to? Yep, the plasma membrane. So if you disrupt the plasma membrane, disrupt the phospholipid bilayer, then you're going to make the cell leaky and everything's going to fall out or leak out, and you're going to have kill of your microbe. Okay, damage to proteins and nucleic acids. How can you damage proteins and nucleic acids? By denaturing them. Generally speaking, we've been using the term denature with proteins, but you can also denature nucleic acids. You can just unravel the genetic material of a microbe and it's going to kill it, or it's going to make it limp along, and it's not going to be reproducing at high rates that we don't want them to. Also, under the category of damage to nucleic acids, you can cause mutations or damage to nucleic acids that's not related to denaturing, that will also cause the death of the organism. We're going to talk more about this when we talk about radiation as a control method. Now let's talk about the various categories of physical methods. First off, in general, physical methods are more likely to sterilize than chemical methods. Now some of these physical methods are not sterilizing methods, and I'll point out to each one of them as we go through them whether it's a sterilizing method or a method that can be used to sterilize, or whether it's more controlling microbial growth without killing them. But we're going to be talking about filtration, temperature, under which category is moist heat, dry heat, and cold. Bet you didn't think about cold as being temperature. And desiccation, osmotic pressure, and radiation. Now the book covers more categories than that, but these are the categories that you need to be concerned about for this class. The first physical control method we're going to talk about is filtration. This is where you take a fluid or a gas, you run it past a membrane in which there are tiny little holes, we call this a filter, and you physically remove the microbes. It's kind of like what we were talking about in the last chapter when we were talking about filtration to remove the microbes to grow them so we can determine growth. This way we're removing them because we don't want them in either the fluid or the gas. Now, we talk about sterilizing fluids or gases with filtration, but technically this isn't the case because viruses can wiggle through those filters. They're very small. So even though we talk about sterilizing with filtration, we really don't, but it's close enough. Examples of filtration that you may already be familiar with are filtering water, such as if you go backpacking and you filter the water before you drink it. That's getting rid of giardia that our friend the beaver here in the picture is putting into the water. You really don't want giardia. Causes backpacker diarrhea, lasts a long time. Another example of filtration that you may be familiar with is running air through a HEPA filter. HEPA filtration is the standard for sterilizing or disinfecting air in hospitals. We also have a HEPA filter in the lab, and also they've been putting HEPA filters into homes and into vacuum cleaners to cut down on dust mites and all sorts of other nasties that we don't want to be breathing in. Moist heat can be a sterilization method. You're familiar with moist heat probably in the area of boiling water if there's a boil order on, or in movies, you boil the water to get the instruments in if you're going to be performing backroom surgery or helping with the birth of a baby. Boiling water actually does not sterilize. It does not kill endospores, and it doesn't kill the endospores of botulism. Therefore, it is not considered a sterilization method. There are two definitions for sterilization. One is complete kill of anything, up to and including endospores. The other one is commercial sterilization, which is getting rid of botulism endospores. Generally speaking, if you eat botulism endospores, it's not going to be a problem. You're not going to get botulism from it. But if you're canning and you have botulism endospores surviving boiling and they grow in your canned goods, then you can get botulism. So you're going, but wait a minute, I've canned before and that's getting rid of botulism endospores. Well, you're right. We're using pressure. Okay? If you add pressure, that ups the temperature. Okay? Because when you boil something, the water stays at a certain temperature at sea level. It's 100 degrees C until the water completely evaporates, and then the temperature of your pot will go up and you'll destroy your pot. But if you add pressure, you can up that temperature up to, in autoclaves, it's 120 degrees C. That's high enough. Okay, you've got the pressure on it, you're keeping the steam in so that the water boils at a higher temperature. So that kills the endospores. This also happens when you're canning in your pressure cooker. Generally speaking, in labs and in hospitals and different places, including dental offices, you will use an autoclave where you have pressurized moist heat, and that's going to kill everything. Now, we also use moist heat in when we pasteurize milk. We're not aiming to sterilize milk when we pasteurize it. We just want to get rid of the microbes that are going to cause disease and lead to increased spoiling. Most of these organisms, with the exception of botulism and some of these others, are sensitive to heat. So you don't have to get it up to as high a pressure as you would in an autoclave or even boiling. But this gets rid of most of your microbes. The milk stays fresh for longer, and you don't have to worry about botulism because we don't keep milk in airtight containers. I should explain here that the organism that causes botulism only grows in airless conditions, and it uses endospores to survive situations in which there's air. So that's why I keep saying you don't have to worry about botulism in containers that have airflow. But pasteurization also gets rid of nasties like listeria. That's been in the news with the cantaloupes. Also E. coli, and other things that are found in the guts of cows. And not to be gross or anything, but whatever comes out of the end of a cow is going to get on the udder. Now, you're probably wondering why, having heard this, there's been a push lately toward promoting the health benefits of drinking raw milk. Well, when you pasteurize, you do lose some of the nutritional value of milk, because when you're denaturing through heat the proteins of the microbes, you're also denaturing some of the proteins in the enzyme in the cow's milk, and it is less nutritious. And with modern dairy practices, the udder is cleaned very well, and there's been a very low incidence of people becoming sick from drinking raw milk. There have been some, and personally, I'm a microbiologist, and I just can't drink raw milk. Just can't do it. I also can't eat sushi. I've been told it's wonderful, it's tasty, very few people get sick from eating sushi, but I just can't do it. A moist heat sterilization is one of the most common forms of sterilization, especially in the lab or in the clinical environment. But there are times when you can't use it. When you have something that will be destroyed or damaged by moisture, Okay, think, well, in the dental industry, generally it's high carbon steel instruments. High carbon steel instruments are not stainless. They rust really well when they're exposed to liquids. You're probably going, why don't they use stainless steel instruments? Well, they don't maintain their edge very well. Also, if you're trying to sterilize a powder, you really don't want to add water to it. So moist heat is not always the best method to use. So you have to take into consideration with all these methods which one's best for the application. On to dry heat. You've actually been using dry heat as a sterilization method in the lab. Can you think of what it is? That's right, flaming your inoculating loop. We refer to this as incineration. You've heated the wire to the point of where it glows and you just burn off those poor little microbial bodies. Now, we can do this when we've got a nice thin wire or a thin surface. We also use incineration when we're trying to get rid of large amounts of protein. If a cow is found to have mad cow disease, it's incinerated. So they take it to a pit. In this case, this is probably a picture from when they were getting rid of herds that had hoof and mouth disease. And they would slaughter the animals, put them in a big pit, completely incinerate them, and bury them up. By the way, if they're getting rid of a cow that has mad cow disease, they're not going to allow the smoke to drift off like this, because the agent that causes mad cow disease can survive certain amounts of incineration, but we'll talk about that at the end of this chapter when we talk about how tough some microbes are. In modern society, we use cold all the time to control microbial growth. Cold does not kill microbes. Kills people, generally doesn't kill microbes. So you can put your milk in the refrigerator and it's good for a couple of weeks, and then what happens? That's right, you're on your way to sour cream or yogurt. We generally go ooh when we toss it out. We can also freeze things, and that preserves things for even longer. Now let's talk about why cold does this. Cold is slowing down the activity of molecules so that enzymes function slower and slower. The lipid membrane moves slower and slower. Transport in and out of the cell is slower and slower, and it basically puts the bacteria into a state of suspended animation. And if you freeze it, that further enhances it. Now, if you freeze things wrong, then you can kill a certain amount of microbes. Murphy's Law, it's generally a problem when you're trying to preserve the cultures, but if you put a steak that is highly contaminated into the freezer and freeze it for long periods of time, it is not going to reduce the numbers of microbes to acceptable levels. It's just not going to do it. Like I said, it's Murphy's Law. So cold is a control method, but it is not a sterilization method. But it's a very effective one. Desiccation is a fancy word for drying out or removing water. Here are some examples of some desiccated food items. As you probably will have guessed by now, desiccation is one of the oldest methods of controlling microbial growth in the preservation of food. We still use an awful lot of dried food items. Desiccation does kill microbes. As you remove the water, you're removing water from the cell, and most of them will die. So this is why dried substances will last for a long period of time. And it's only those that are sort of dry, like the raisins off to the side, that you will get organisms that are resistant to osmotic pressure, that are either halotolerant or tolerant of high concentrations of sugars, like what you have in your raisins, are going to be able to survive on it. So that's why things that are dried out have a tendency to go moldy. Fungi, yeasts are osmotolerant. So that's using desiccation to preserve foods by decreasing the number of organisms that are in your food items and preventing other organisms from coming by and eating them before you get a chance to. Desiccation has varying results depending upon the toughness of the organism. Gonorrhea will resist drying for about 1 hour. So you're highly unlikely to get gonorrhea from toilet seats, especially if you make sure they're dry. TB, on the other hand, they have a waxy coat. Remember that mycolic acid the cell wall of acid-fast bacteria. This prevents desiccation. So even when you're drying sputum that has come onto a table or something like that, you're not drying it, it's just drying. Then the organism resists that drying process and can survive that for long periods of time. Also, to remind you about Chapter 6, we use desiccation as a preservation method for pure cultures. Do you remember what that was? That's right, lyophilization. It's a fancy word for freeze drying. Osmotic pressure is related to desiccation. Osmotic pressure is where you're putting a higher sugar or salt concentration outside of the cell, drawing the water out of the cell, and it results in most of them dying unless they're osmotolerant. Now, desiccation, we're removing water to achieve the osmotic pressure. Okay. Osmotic pressure, when we refer to that, that's usually where we're adding sugars or adding salts to something to increase the osmotic pressure. We're doing this without removing the water. Honey is a prime example. This is where we add honey or sugars to substances to make them less palatable to the microbes. For example, if you're trying to preserve your fruits from your garden this summer, what are you going to do? You're going to make jams out of them. Actually, you could make juices and just cap it and can it, but traditionally you didn't have that as an option. So what we did is we added a whole bunch of sugar, and that increases the osmotic pressure, and you end up with preserved fruits. Also, hams. If you salt a ham, and hams are all salted, you're adding salt to it, increases the osmotic pressure, makes it so microbes don't live there, and we preserve our foods. Now, we've gotten away from doing an awful lot of this now that we have refrigeration. We don't like things as sweet. We don't like things as salty because we don't have to do that to preserve our food. We still like honey and we still like sweet things, but it's a little less prevalent. Now to the last physical method, using radiation. You're probably going, radiation! Radiation has gotten a bad rap through various events in Japan recently, and also from atomic bombs and what have you. Radiation has gotten a bad rap. But radiation is very useful in controlled ways to control microbial growth. So let's talk about light. Visible light is the spectrum of light, the wavelength of light that you can see, and it does not kill microbes. If we move to shorter wavelengths, more energetic wavelengths, then we start killing microbes. So let's talk about UV. UV radiation is non-ionizing. In other words, it's not removing an electron from an atom, so we're not creating ions. What we're doing is we're creating mutations or bumps in DNA by either denaturing it or by causing bonding between bases that shouldn't be. We'll be talking about this more in Chapter 8, but I want to introduce it here, and I do want you to know that UV radiation is non-ionizing. Now, this is the wavelength that is bactericidal. We use this in microbial biosafety hoods. We put a UV light on it, kills just about everything, and is considered a sterilization method. The problem is it doesn't penetrate. You can use a piece of paper to block UV radiation. Makes you feel better about going into the sunlight, right? So, yeah, if you wear clothes, you're less likely to get burned. Okay. Now, if we move up from that, we're going to skip X-rays because they're not commonly used. If we go to gamma rays, you're probably familiar with gamma radiation coming from outer space, and we use telescopes that pick up gamma radiation to see into distant galaxies. We can also use this to sterilize. Gamma rays are ionizing. Okay. The rays are energetic enough that they're going to knock electrons off of molecules, and we're going to create ions where they shouldn't be. If you create ions in the plasma membrane, then your plasma membrane breaks down. If you create ions in proteins, you change the structure. If you create ions in DNA, you break up the DNA, you cause mutations. Okay, it's sterilizing. Gamma rays penetrate further than UV rays do. So in lab, when we've used those single wrapped pipettes that are in the paper, it's paper on one side, plastic on the other, those have been sterilized by gamma radiation. The radiation goes through, kills the microbes, passes on through, it's no longer there. The item is not radioactive. It's only radioactive if you have an atom that's giving off radiation stuck on there. But when the radiation passes through, it sterilizes, generally does not distort the plastic, and we consider this a method of cold sterilization. We use this when we can't autoclave something and you can't boil it, okay, because it's sensitive to heat or moisture, and we can sterilize powders and all sorts of good stuff. Now, in Europe, they sterilize food by using ionized radiation, by using gamma rays. They wrap the item in plastic, they zap it with gamma rays, and they can put milk and raw meat and all sorts of good stuff on the shelves, and it does never rot. Now, it may break down chemically, and it may go rancid, in other words, but it's not going to rot. It doesn't have microbes in there, and you don't have to worry about E. coli or listeria or all sorts of other stuff. All right, that's it for the first half of Chapter 7. Stretch, take a break, think about something else, come back and we'll talk about chemical control methods.